Good morning. So, we in the previous lecture we studied about the Ugi spillway. Now, we are going to work on the Chute spillway, and the Chute spillway has some design is a lengthy design. So, we are going to split the lecture into two parts, that is Chute spillway part 1 and the part 2, and at the end we are going to cover the energy dissipation of this spillway. So, the Chute spillway is an open channel like structure which is constructed on a steep slope of a gully face with a suitable inlet. So, here is the inlet point and outlet. So, Chute spillway is mostly suited for earthen and the rock-filled dam, and it is also known as an alternate name trough spillway. And Chute spillway is the simplest type of spillway which can be easily provided at a rural area at a low cost. So, Chute spillway is also known as the west weir, and it is constructed in continuation to the dam at one way, and it may be called as a flank weir. So, if there is a dam here, so it can be constructed at the end of the dam. So, here it is called as the flank weir, and it is also constructed in a natural saddle at the bank of a river separated from the main dam by a high ridge. In this case, it is known as saddle weir. So, this is the saddle weir here, and Chute spillway is essentially consist of a steeply sloping open channel placed along the dam or abutment through a flank or a saddle. So, the Chute spillway generally leads water from the reservoir to downstream. The base for the channel is usually made of reinforced concrete slab around 25 to 50 centimeter thick. The chute is sometimes of constant width, but is usually narrowed for economy, for the trade off between economy and the best design consideration, and they have a widened near the end to reduce the discharge velocity. Now, for designing of Chute spillway, we also need an expansion joint, which are usually provided in the chute at an interval of about 10 meter in either direction. So, the expansion joint should be made of watertight so as to avoid any under seepage or any troublesome effect. So, under drains are also provided so as to drain the water which may seep through the trough bottom and the side walls. The under drain may be in the form of perforated steel pipe or clay tiles or rock filled trenches, and the shape of the chute must be high enough and should be at least be able to maintain a supercritical flow to avoid any unstable flow condition. So, here a sample chute spillway is shown. So, this is the inlet of the spillway, and here a Ugi curve is placed here, and this is the steep slope channel, and this is again flow to an outlet. So, this is a way a chute spillway looks. Now, the basic component of the chute spillway, as you can see the structure here, the entrance channel or the approach channel, then there will be a control structure, which is here an Ugi curve is placed, and there are many control structure, but here is shown as Ugi curve. And then chute channel or the discharge carrier, which is this part, the steep slope channel, and the energy dissipation arrangement in the form of a stilling basin. So, this is this part, the energy dissipation arrangement is here. So, there are 4 basic components for the chute spillway. Now, coming to each of these components one by one, first we will start with approach channel. So, what is approach channel here? It leads the reservoir water up to the control structure. It may be straight or curved in a plane, and it is generally in trapezoidal shape, and the slope is kept as 1:1, and its banks may be parallel, convergent, divergent, or combination of these, and may be vertical or sloping. it may ensure minimum head loss through the channel and to obtain uniformity of the flow over the control structure. Now, how to design the approach channel? The friction head lost in the channel up to spillway crest may be calculated by Manning's equation, which is HF is the friction head, SF multiplied by L, where SF is the energy gradient between 2 points, N is the Manning's roughness coefficient, and velocity V is the velocity of the channel. So, this is by simple equation here. V equal to 1 upon n r to the power 2 by 3 and s to the power 1 by 2, which is plugged here as a so here it is shown. So, you plug here, it is V square n square, and then the s you calculated here. So, if you square it, so it will be 1 upon n square r to the power 4 by 3 and you get the value of s. So, where s is plugged here. So, in this way we can get the HF value. Now, the control structure. So, there are different control structure. Since the chute spillway is provided in a flank or saddle, oogie wear is generally provided as a control structure. The profile of the spillway is made in accordance with the shape of the lower nappe of the free falling jet. So, theoretically, adaptation of such profile should cause no negative pressure on the crest, and negative pressure causes what? The fluctuation of head and thereby instability of the flow and increased load on the structure. So, here you can say the profile of the oogie wear to be used as a control structure. So, here h is the height of the crest from the bed level, as we explained this also in the design of oogie spillway. Hd is again the design head, Ha is the velocity of approach. So, He is a combination of Hd and Ha, and this is the downstream profile here, the downstream profile here, and the upstream profile should merge with downstream profile at an 1:1 slope. And here there will be a discharge carrier, and a gamma is the radius of reverse curve which joins the downstream profile to discharge carrier. So, this is calculated using this term gamma. Now, design of the crest profile. So, now if HA, HE and H are known, then we have to decide the upstream profile and the downstream profile. So, the equation for downstream profile of the low oogie wear is given in this following equation. These are all empirical equation which is fixed by US Army of Corps through some studies, and H by He range of values are given here. Sorry. And for different values of HA by He, there are different value of H by He, and corresponding equation for downstream profile are given here. Now, the coordinates of the upstream profile for the low oogie wear. So, x by He, and if Ha by He is 0 and Ha by He is 0.08 and Ha by He is 0.12, how this profile varies. So, this kind of table is given for calculating the design problem. Now, chute channel or the discharge carrier design. The water spills over the control structure flows through the chute channel, and the minimum slope of the chute is governed by the condition that the supercritical flow must be maintained. So, it is generally rectangular in shape with a bottom width is equal to L. Now, coming to design of the vertical curve of the chute. So, this is a concave curve. So, in this case a concave curve was assumed. So, this is the concave shape. Whenever the slope of the chute changes from steeper to milder, a concave vertical curve shall be provided. So, here we given a concave vertical shape, and in no case in the radius. So, this is a concave. So, this is a curved surface. So, this is the radius. In no case this radius should be less than 10 d, where d is the depth of water here. So, minimum this curvature is given as 10 d, and this is a steeper slope, this is a junction point, and this is a milder slope. So, it will gradually go like this from steeper to milder. Now, the convex curve. So, this case whenever the chute changes from steeper to milder, concave curve shall be provided. Now, in which case the convex curve. So, whenever slope of the chute changes just opposite, milder to steeper, in that case a convex vertical curve should be provided. So, this is the convex shape here. So, here the slope going from milder to steeper, and this is the junction point. So, the equation for this is given as y equal to minus x tan phi and minus x square of 4 h d plus h v and cosine square of phi, where this phi is the slope angle of the flow at upstream, and d plus h v is the specific energy of flow at junction point, and k is assumed generally as constant is 1.5. So, using this equation we can calculate the slope, the y at a given x. So, Stilling basin. Stilling basin we keep it for energy dissipation, which is the last component of the spillway. So, this is a structure in which energy dissipation action is confined, and in this energy dissipation structure an aprons are provided with auxiliary devices. So, what are the auxiliary devices here? Chute blocks, seals and baffle walls, these are usually worked as an auxiliary devices, and it helps in dissipating the energy of flow by offering resistance to the flow. So, this is for the Stilling basin. Now, what happens to the Stilling basin? So, once the flow of water at a high speed falls and there is a occurrence of hydraulic jump, as you know from the principle of fluid mechanics. So, hydraulic jump principle, it is the ratio between y 2 and y 1, where it is a critical depth, and which is again a function of the Froude number. So, y 1 is pre-jump depth and y 2 is the post jump depth, where y 1 and y 2 are the conjugate depth, and a Froude number is given by the ratio between v divided by acceleration due to square root of acceleration due to gravity and y 1, what is the pre-jump depth. So, depending upon the Froude number, the velocity of flow can be critical, subcritical or the supercritical, and based upon the velocity of flow, and we can design the Stilling basin. So, different jumps are classified according to F1 or the Froude number, and accordingly Stilling basins are provided. So, F1 if it is 4.5 is a supercritical flow, and USBR Stilling basin 2 is used in this case. So, this is the kind of Stilling basins are provided, and okay, sorry. So, if F1 is greater than 4.5, the jump is well balanced and steady. So, in this case the Stilling basin 2 is provided, and however, if the jump is between 2.5 to 4.5, it is oscillating, and in this case the Stilling basin 4 is provided. Now, the length of the basin varies between L, this is the equation how that we design the length of the basin, which is a difference between y 1, that is the pre-jump, and y 2 is the post jump, and which is multiplied by 5 is the length of the basin. And for basin 2, depending upon the Froude number, we again fix the length of the basin like this. So, if the Froude number is 4, So, we generally kept as 3.6 of y 2. If the fraud number is 6, we kept is a 4 times of y 2. If it is 8, 4.2 y 2, and if it is more than 10, then we generally kept as 4.3 of y 2, where y 1 is the pre-jump height or a depth, and y 2 is the post jump depth of the Stirling basin. So, thank you.